Hello, everybody. My name is Zhuo Xu, and I'm a PhD candidate from Norwegian University of Science and Technology, Department of Mechanical and Industrial Engineering. Today, I will present the topic of scale and thickness effect on the mechanical behavior of structural parts fabricated via fused deposition modeling. I would like to take this moment to thank my supervisor Javad Razavi. I couldn't accomplish this work without his assistance. So this is the outline of this presentation. First, I will present some background and motivation of this research, and then I will show you some of the FDM fabrication process, and then I will be presenting experimental procedures and the results and discussions, and finally the conclusions. So the aim for this presentation is to investigate the influence of scale and the thickness effect of FPLA specimen fabricated with FDM technology. So this is the background of FDM. FDM, as we know as fused deposition modeling, is one of the most widely used additive manufacturing process in the world. It is also a rapid prototyping process that can fabricate the physical model directly from CAD without using any tooling or fixture. And it is a technology where the melt extrusion method is used to deposit filaments of thermoplastic according to the specific pattern, which means the movement of nozzle. As we can see from the image here, this is an example illustration of FDM printing technology used in pharmaceutical fields. It has many aspects, including environment, filament, hardware, software. So this is the motivation of this research. So the geometry and the thickness of the component can have a direct influence of the distribution of, for example, internal porosity, surface quality, geometrical accuracy, and residual stress. Okay, and these factors could result in variations of the mechanical property with the input geometry. So therefore, it is very important to understand the link between the mechanical behavior and the scale and the thickness effect to be able to improve the design technique and the manufacturing process. So these are the test specimens we have selected based on the ASTM standard Tensile test specimen for all five types. So we chose type 1, which means all the parameters are listed in here. And these are the fabrication process and the test specimens. So for the 3D printer, we used the Prusa i3 MK3. So it is a very good desktop level 3D printer with very good accuracy. The filament we chose is 3D net, and the color is natural because we have done the research, we have done the literature review saying the colors will affect the mechanical properties. So in order to eliminate this effect, we chose natural color. And for the slicing software, we use Ultimaker Cura. It's an open source slicing software. And for the test specimen, as I mentioned from the last slide, it's standard ASTM. These are some of the process parameters we used for the fabrication. For the thickness effect, as you can see from the table at the left top corner here, so we have determined for 4 thickness, which is 1 millimeter, 3 millimeter, 5 millimeter, and 10 millimeter. And the second table below is for the scale effect. So the largest scale is the one same to the 3 millimeter specimen. and then we scale it down to 50% and 30%, and the rest number indicates the cross-sectional area and the gauge length for each test specimen. And the table on the right side is the printing process parameters as some major important parameters, like the layer height. We used 0.1 millimeter. That's the best layer height we can achieve so far with this printer with good quality. And the infill line distance is 0.4, and the infill density is 100%, because we try to infill as much as possible to keep it the mechanical property similar as the solid part, but at the same time maintain the quality of the specimen. Also, the raster angle is around is plus minus 45 alternately for each layer. So this is the tensile test machine and the parameters we used. We used the universal MTS tensile test machine. It has the maximum load cell capacity of 5K newtons. And for the sampling rate, we chose 10 Hertz, which means 10 data points were recorded for each second. And for the tension rate, because PLA is sensitive to the tension speed, so we chose 2 millimeter per minute in this case to avoid too fast or too slow conditions for the tensile test. And all the fracture surfaces were examined with an optical microscope after the test. So these are the specimens after fracture. This is for the thickness effect. I chose 3 out of 5 to be listed in here. As you can see, all the fractures surface are within the gauge area. Some are more close to the middle, and some are within the edge of the gauge area. And similarly, these are for the scale effect. All the fracture surfaces are in the gauge area. Some are more towards to the middle, and some are in the edge. The detailed reason I will explain later. And this is the one possible reasons to explain why some of the specimens have the fracture position near the edge of the gauge length. So for each layer, for the printing, for the Cura software, instead of starting from the end, it actually starts somewhere in the middle for every single layers. So that may cause some defects in here. And we can make assumption here. The dimensions of the voids are identical for each scale because the same process parameter were used in this case. And these are the fracture surfaces with the thickness effect. As you can see, the arrow indicates here there are some defects such as voids or during the fabrication process. As you can see, visually, if the thickness is getting larger, then the defects will decrease. Similarly, for the scale effect, as you can see, here we have presented the scale from 30% to 100%. So as you can see, from the 30% of the specimen, there are much more defects during the printing process than for the rest. So we also used digital image correlation, DIC for short, for analysis. So for subset, we used 29. The subset means the area of the dots which was being tracked by the software for DIC. The larger number it is, the larger area it has, but also it has the larger uncertainty as well. And for step, we select number 7, which means for every 7 points, the software will take in the average and use the average data to do the measurement and the calculations. And as you can see, the label here, EYY, means the engineering string along Y direction. So as we can play the animation here, but as the time goes by, there is some deformation in multiple middle parts of the specimen, and the propagates to both sides. And then if it reaches at some point, as it goes to different color, which means the string is getting larger, and then it will have the largest string showing here, which means this is the area that's most likely to get broken. And these are the methods of calculating Poisson's ratio. And for the DIC, we can select one small area somewhere in the middle, and we can do the calculation for the Poisson's ratio. Okay, so these are some images of the DIC and the comparison corresponding to the real specimen. You can see from here the highest stress area is showing in here, and also that's the area for the fraction. And as you can see from this image, multiple areas of the high stress, so which means the specimen could be breaking from here and somewhere in here as well. So there's also a possibility, but the specimen ending up breaking in here. So this is the result for all 4 thickness, and as you can see from this stress and strain plot and the data we have reported in this table, as thickness increase, the ultimate tensile strength also have the tendency to increase, even there is not much difference between the 3 mm one and the 5 mm ones. And also the elongation at failure also increases when the thickness increases. So these are the results for scale effect. As we can see from both of the figure and the table, the yield strength, ultimate tensile strain, and the elongation increased when the scale is increased. But the Young's modulus is keeping constant as the scale changes. And for that, we can get some conclusions. First, there is a high degree of association between the tensile property and thickness. So in detail, specimens with larger building thickness experience both higher tensile strength and larger elongation failure due to the possible reasons. First, layer quality, because for 3D printing, especially for the FDM, first layer is really important to print and to optimize, and sometimes it can be affected by many other factors. So there's uncertainty in first layer quality. And next is because of the higher number of layers can result in higher temperature gradient in the layers, which can also lead to the increase in the diffusion process between adjacent layers. And this will result in decreasing the void ratio and improving the strength of the bond, which will improve the ultimate tensile strength as the thickness increase. And second, as you can see from the table I showed earlier, Young's modulus is slightly decreased with the increase of the thickness. And there's a possibility that the specimen tend to have less defects and voids per unit volume when thickness increase, according to the image. So for detail, we still need to do the voids and the defects analysis for the fracture surface to confirm this hypothesis. And the standard deviation for the mechanical properties has a tendency to decrease when the thickness increases. So there's a less discrepancy in the data due to the possible reason that uneven temperature distribution on the building plate will have less influence. Because for the specimen fabrication, we have 5 specimens for each case, and we fabricated 5 of them on the same plate, so there might be some uneven temperature distribution on the plate, so that may cause the discrepancy of the data. And when the thickness increases, that the effect of the influence of that is getting smaller. So similarly, these are the conclusions for scale effects. First, specimens with downscaling experience both smaller ultimate tensile strength and lower elongation at failure, as well as yield stress due to the possible few reasons. First is the first layer quality. As we know, FDM printing is a technique that the first quality is very important to the overall printing quality, and it is influenced by so many other factors. That's why the first layer quality is one of the possible reasons to affect the scale effect. And the second is the possible weak spot near the edge of the gauge length, as demonstrated before. And another reason is it is possible that specimen tends to have more defects and voids per volume when downscaling according to the fracture surface images from the microscope. And also, for the standard deviation of the mechanical property like elongation at failure, yield strength, and UTS, they increase when downscaling due to the reasons. First, it's the uneven temperature distribution on the building plate when fabricating. And second, because the specimen gets smaller, so there's a higher chance of misalignment when testing. This is the end of my presentation. Thank you for watching, and if you have any questions, please contact me.